We're going to start chapter 9 with an exploration of something we already know about. Nucleophiles. We're going to classify the following nucleophiles according to their type: strong, moderate, or weak. I grabbed this from the textbook. Strong nucleophiles, moderate, and poor, which is, yes, so you guessed it, another way of saying weak. And there's two types of reaction in this course, in this discussion. SN1 versus SN2. And SN2, I like for this discussion to start here because the nucleophile attacks a carbon that has a halogen on it. Br is a good one. Yeah, let's make it a stereocenter even. Yeah. And we'll go CH2, CH3. And what's that fourth line going to be? CH3? Why not? And what happens is you get a backside attack. This leaving group leaves. And here's your whole mechanism in a nutshell. New bond from the nucleophile. We'll say it was an anion. So when it's got its new bond, it's not an anion anymore. H got pushed way over here. CH3 is up here now. 2 CH3 here. And get that. And we already looked at what happens to a stereocenter. It used to be R. When you're done, it's S. Because there's a backside attack. And I think we did a video with that showing it flipping, hopefully made it look like an umbrella flipping with the wind or the big bad wolf. I think we used that discussion. The bromide is still, it's there, but it's now the leaving group. It has left the building. And there it is. LG stands for, from now on, leaving group. And we already discussed excellent leaving groups are the conjugate bases of the strong acids. That's one of them. You can go to the table on page 121 of your book and find the other 6. Chloride, iodide, perchlorate, nitrate, hydrogen sulfate, tosylate, TSO minus. And that's the SN2 story. And the 2 comes from the fact that there are 2 molecules in the RDS. There is only one step here. It's shown. One reaction. So this is the step. And it's also the rate, because it's the only step, it's the rate determining step, right? There's no other step to compare it. SN1, its name might confuse you because it has 2 steps. That's not what the 1 is about. The 1 is, there's only one molecule involved in the rate determining step. So I'm gonna switch. And we're gonna make sure this time I don't really want the same molecule, yet I have it. I just did a quick edit here. Quick edit. Sadly, it's not a stereocenter anymore. My quick edit wasn't very nice. Sometimes the easiest way out, not the best way out. There. I wanted a tertiary carbon that was also a stereocenter. That was my issue. Same kind of nucleophile. Here we have a slow first step. Slow first step, and this is what's happening. It's different than the previous one. Can you tell me the differences so far?
There's no backside attack.
There is no backside attack. That's correct. I don't know if that's what you said though. Yeah, there's
First up is BR lead.
yeah, BR minus just up and leaves on its own here. How many molecules were involved? Not the nucleophile was not necessary for this, was it? Only Rx is involved, and I don't think we've used the short form Rx yet. R is a carbon, X is a leaving group. Okay? When R is tertiary, and you get this intermediate here called a carbocation. No carbocation here. No carbocation. That is a huge difference. The consequences of that difference are as follows. Because there's a backside attack on a chiral species, you get only one product. In this next one, which is the first one, you can have the nucleophile half the time it comes in from the front. In which case you will get this species came in from the front. There's your new, and you got your ethyl. Maybe I'll make that a dash. Ethyl here. Why not go stick figure? Since we're here. Stick figure, stick figure. There you go. And 50%. From behind. Why is it a 50-50 proposition?
Because it can be R.
Why can it be R or S? Why? Well, why? The previous one could have been R or S, but it only picked one. The approach of the nucleophile is dictated by the leaving group in the SN2. Is there a leaving group involved in this last step that I'm doing right now? The fast step? I didn't label it as a fast step yet. I'm going to. And that's a wedge. From behind, you get that. I'm assuming the nucleophile has the highest priority, in which case the first one is S and this one is R. So in SN1, you get racemization of the stereocenter, right? What's that mean? It's a new word, racemization. I bet you can figure it out. Chapter 3, racemic mixture, 50-50 mixture of enantiomers. Racemization is making a racemic mixture where you did not have one before. So you took a molecule that was a pure stereocenter. In this case, it's S. When you're done, you got a 50-50 mix of two products, 50-50 S and R. Very different result in an SN2. SN2, you have control. SN2, if you have a fixed stereocenter to begin with, it's R, you're guaranteed a fixed stereocenter when you're done, 100% yield, only S, no R here. Yes. So we have to become experts at knowing which of the reactions is happening. And studying nucleophiles is one thing that can make one of these happen over the other. Solvents is another thing. Carbon with the leaving group is the first thing we look at. Okay. So let's just do one thing at a time. Nucleophile. Can you tell me something that all the very strong nucleophiles have in common? Every single entry at the top of the screen has one thing in common. An anion, yes, a negative charge. But read carefully the whole document here, the whole list. There is an anion on the list that is not at the top of the list. It's in a different category. Which one is it? The moderate RCO2 minus carboxylate is an anion that's not as reactive as any of these because it's doing this. It's resonating. That means the anion is not stuck on this oxygen. That means the oxygen's less reactive. It's spending less time with a minus charge. You would be less reactive if you were spending less time with a minus charge as well. Okay, so I'm just trying to help you learn this table because you're not given this table on the test. No. I mean, you already know if it has an anion, it's going to be a strong nucleophile unless it's a carboxylate. That's not memorizing 10 things like you think it is, right? There you go. What about all the moderates? They're neutral to start with, right? Neutral. And the poor are also neutral. So how are you going to distinguish? If it's neutral, you're thinking either moderate or poor, right? What's the way you distinguish this group from this? Well, how about this big group from this littler group? Smaller group, sorry. They have either a neutral sulfur or a neutral nitrogen, then you're moderate. That's two things. That's not 7. 2. One thing, neutral sulfur. One more thing, neutral nitrogen. Not 7 things, it's 2. And then neutral oxygen, not 3 things. Or if you consider a number of R groups, there are millions of things, okay? Any neutral oxygen's poor. Now, the question of the day. Given that information, which reaction is going to speed up if the nucleophile's strength is increased? Is it going to speed up the rate determining step of this if you use a stronger nucleophile? Heck, this thing don't care about the nucleophile. That's what the mechanism says right there. I don't care about the nucleophile. I'm just going to become a cation on my own. I don't care what nucleophile's around. So the only thing this reaction depends on is the carbocation stability. SN1 only happens with tertiary RX or secondary RX with a polar protic solvent. Oh no. That's our next activity, by the way, solvent. But if you want to know when SN1 happens, that box has got it covered. So in this very example that we have here, it's tertiary, correct? That's when SN1 happens because it's all about the stability of carbocations, this rate determining step, isn't it? Yeah. From this day forth, from now on, CH3 plus and CH2R. I want to point out that's a primary C plus. R, and you guys all like when I do this. Well, not all of you. but it really gets the point across to my Arabic students, well, my Muslim students. Haram, right? You don't want to put a methyl cation on your test from now on, or primary. They are too unstable to exist. That's all I'm trying to say there, guys. So you didn't know this before. Yellow's a bad choice. You got a yellow already. Maybe blue. Forbidden, okay? Don't put these on test. So, cation. SN1 needs to have at least a moderately stable cation. Tertiary is pretty good, right? Secondary, not as good. So it needs help. What kind of help is it going to get in our next activity? Polar product solvent is going to help out enough so that the secondary cation is okay. SN2. I did a secondary cation, and this one would not have a polar product solvent. Solvent is not polar product. We're learning everything kind of on the fly here. Solvent is not polar product. We haven't done any solvents yet. There's no solvents on this page yet. So if you have a secondary carbon, SN2, if you have any solvent that's not polar product, tertiary, you're going to have SN1 no matter what. Secondary, you would have SN1 only if you had a polar product solvent. That's a lot. Let's finally do this activity. Now he's telling his students they didn't have to write anything at the bottom of the page. I should have said that earlier. I mean, it's good to write things down. You know that. But really, I only need the answers to our activity, which we're ready for. We've got azide. So that's KN3 minus. Circle it. See it right there? Strong. You don't have to use very strong. You can use strong. Yeah, piece of paper, Roman numerals 1 through 6, and the answers. That's all we need. Classify the following nucleophiles according to their type. You don't have to copy that down. Strong nucleophile, it's right there. Which reaction is favored by that nucleophile? Well, guys, SN2, it's very important the nature of the nucleophile. It's involved in the rate determining step. This is the only rate determining step. Here's the RDS here, nucleophile not involved. So nucleophile strength, not important for a tertiary. Nucleophile strength for SN2. And if you got a strong one, you're making the SN2 faster. If you got a weak one, you're slowing down the SN2 so much that you might stop it. That's what weak means. Slows down the SN2 reaction so much that it may stop. Okay? So strong nucleophiles love SN2. So you're going to say SN2 every time you do a strong nucleophile. Got it? SN2. Can we go and find more strong nucleophiles on this handout? I think there's 2 more. Notice he didn't say 3. I see 3 potassiums. You say, oh, there's 3 anions then. Dr. Whitaker, the anions are all strong nucleophiles. Which one of those 3 ones with potassium that remain is not a strong nucleophile? Number 4. 4 is moderate, circled in purple. Moderate. And it's this category here. I'm trying to get it. And it's the purple. And that's when you say the third option. Aha. So doesn't that sound like you're in the middle, right? Mabaraf in Arabic means I don't know. You can write Mabaraf on a test, or you can write SN1, SN2 question mark. They say the same thing. SN1 / SN2 question mark says the same thing as Mubarak. Okay? I'll even write Mubarak the first time. Oh, it's double A.
Wait, how did you just say that you don't know?
Oh, the category moderate means I don't know. If you approach somebody and they're a moderate, they're not going to be strongly favoring one of the candidates, right? They want the one in the middle. Okay. KOCH3, that is the pink category. Strong, SN2. Strong always favors SN2. And let's pick the other strong. Acetylide. R equals H for acetylide is baby blue, I think we haven't used. And it's strong SN2. Save the best till last. Number 3 is in the moderate category, isn't it? And it's got a neutral nitrogen. I'll pick the circle too, in yellow. It's a primary amine. I'll circle the primary amine. And that one is moderate. What's your conclusion for moderate? Would she like saying Mubarak? Okay. Yes, you got it. Weak. You slow down the SN2, so by default, which one are you helping? By hurting one, you're really helping the other, right? By default. SN1. There you go. In black, we'll circle the alcohol and go for black here. Right there. Good video. I think we'll count that. Maybe as a double with all the time we spent. There we go.